Us today. I'm here today with Professor Mike Lockwood, and he has a really good presentation prepared for us. I'm really looking forward to hearing what he has to say, and also I'm looking forward to receiving questions from the audience. So if you have any questions, please do send them in, and we will leave about 10 minutes at the end to answer your questions. But without further ado, Mike, the floor is yours.
Okay, thank you very much, Anya. I just start a stopwatch so I keep to time. Okay, welcome everybody. Today I'm going to start with a well-known way that a program started. Now, those of you who ever watched Star Trek will know that every episode starts with the wonderful byline, "Space, the final frontier." And that is very clever. What the authors were doing was that they were tapping into something that started way back in 1897 with an essay written by an American historian called Frederick Jackson Turner, who wrote this essay called "The Frontier in American History." And it's widely quoted, particularly by politicians in America. And an important point about this, though, is that it's partially quoted, it's selectively quoted. So in his thesis, Turner says, "The frontier individualism has from the very beginning promoted democracy." That sounds great. But he goes on to say, "But it has also made that democracy strong in selfishness and individualism, intolerant of experience and education, and pressing individual liberty beyond its proper bounds. Its tendency was antisocial. It produced antipathy to control, and particularly to any direct control. It has permitted lax business honor, inflated paper currency, and wildcat banking." Now that sounds a bit familiar to me at the moment. So let's dig a little deeper into what he meant and what others have meant by frontier mentality. All these authors have addressed it. Donald Worcester, he particularly showed how the frontier mentality led to bad farming practices that led to the Dust Bowls. Okay. Patricia Limerick has concentrated much more on what it meant for indigenous peoples, okay, and the lack of law, basically, in the Wild West. And then recently, Karina Keskitalo, who's an academic at Umeå University, she's talked about frontier thinking, and she makes the important distinction between conservation frontier mentality, where you go to the wilderness to try and protect and enjoy the wilderness, and colonizing, where you see the wilderness as the boundary between civilization, and you're going to move that boundary to bring the wilderness into civilization and exploit it. And that's a very important distinction, I think, in terms of space as well. So the other side of this starts really with the most amazing quote from Fred Hoyle, the British astronomer, who in his series of lectures on the BBC Radio, what we'd now call Radio 4, home service it was then, called "The Nature of the Universe," he made the most amazing prediction. By the way, those were the lectures where he introduced the term "the Big Bang," which he meant sarcastically. He didn't believe in it, but it was a sarcastic comment. But what he said was, this is in 1950, "Once a photograph of the Earth is taken from outside is available, once the sheer isolation of the Earth becomes known, a new idea as powerful as any in history will be let loose." And what he meant was environmentalism and sustainability. And that's what he was talking about. And he was right. I remember the huge effect that Earthrise picture had on my parents when it was published in the Cullimer supplement to their Sunday newspaper. They saw the Earth in a different way from that moment on. So here is that picture. It was taken by William Anders from Apollo 8 on Christmas Eve, 1968. And Anders, after they landed, came up with this amazing quote. He said, "We came all this way to explore the moon. And the most important thing is that we discovered the Earth." Now, this picture has been in the news a lot this week because of the Artemis mission. And I'm going to show you a similar picture. We call this picture the Earthrise picture. They have coined this picture the Earth set, because it was the moment the Earth disappeared behind the moon for them. But actually, the most important image, I think, that came out of Artemis is this one in the top left corner. And this shows the captain of the mission, who was called Reed Wiseman. Now, there's a great name if ever there was one. And he's looking out the window, and I know what he's thinking about. I know he's thinking about back home and his two daughters, Ellie and Catherine, who he's brought up for the last 5 years, because his wife, Carol, died early of cancer about 5 years ago. And in fact, one of the things his crewmates did was they proposed that a new crater which just on the far side of the moon, so sometimes you'll be able to see it from Earth as well as from the far side. And they want it to be named Carol after her. And I think, referencing William Anders's comment, that I would say about Artemis, they went all the way to the moon. And the most important thing is they helped us rediscover our humanity. And at this time, we need that. We need it badly. Why do I worry about frontier mentality? Well, I'm going to briefly tell the story of the American bison. These incredible animals used to wander across the whole of the North American continent. There were probably, well, we know from records of bones that there were about 80 million of them in prehistory. And if we look at the numbers of them, we see that 60 million, I beg your pardon, and they fell from about 60 million in 1800. And by 1900, we knew of 350 beasts, okay? And since then, they've recovered to about 4,000. And this map here shows you where they were in prehistory, pardon me, from the bones. And the map on the right shows you in light brown where they were in 1850, in the middle brown in 1870, and in the dark brown, those few spots were all there were by 1890, okay? And what's interesting is that I've marked on here the railways. The Central Pacific Railroad met the Union Pacific at Promontory Point's summit in Utah, a famous meeting that linked the West Coast to the center of the USA. And you'll notice actually that the bison loss happened specifically around that railway. And if we actually look at the curve, oh dear me, sorry, I'm trying to use the pointer, but I keep messing up. So the number of bison killed in their millions peaked about here. It then went up again because all over the eastern center of the USA, tourist agencies opened up so that people could go and shoot bison. Okay, they were sponsored by the government because of course there was a political element to this. You were removing the basic food source and lifestyle of the Native Americans. It then peaked, as these things always do, as bison got harder to find, but then the railway opened and you'll see it peaked again before this catastrophic fall. Okay. Now, why was that happening? Well, that's best told by this woodcut from somebody who clearly disapproved. And he called this woodcut Massacre from the Train, because the trains would stop, they would equip people with a Stetson and a shotgun, and they could pretend to be frontiersmen and just shoot bison. So if they saw bison, they'd stop the train and shoot them. Okay. And this is a picture taken from the train, from the railway line, and all you can see are the whitening bones of bison. It's unbelievable, the scale of the massacre that went on. And actually, these are all bison skulls at a glue factory where the bones were taken to make glue. This was in Michigan. So this was a horrific scale, completely unsustainable thinking, but it was all done by people pretending they were on the frontier. So now my point is that space is not the final frontier. Okay, near-Earth space in particular is a very fragile resource that we already are there. We already use it. We use it for communications, navigation, astronomy, Earth observation, resource exploration, disaster management, broadcasting, global internet. We make new materials when we're in space. There's zero gravity experiments, and many other things that we do in space. And all of those things are threatened by space junk. It's an existential threat for all of those activities. And that's the main point of this talk. Now, I wanted to just talk a little bit more about frontier mentality and people who take the one half of it, the inspirational, it's established democracy side, but not his caveats and the Frederick Turner's caveats. And in particular, talk about Peter Thiel. Now, Peter Thiel is very much the high priest of frontier thinking. He's always talking about innovation on the frontier. Okay. I'm just going to take this second quote from him. I believe we're in a world where innovation in stuff was outlawed. It was basically outlawed in the last 40 years. Part of it was environmentalism and part of it was risk aversion. Now, that is the most extraordinarily selectively myopic statement that I know, because the 40 years he was talking about was the 40 years in which the internet was developed. And Peter Thiel made his fortune, along with Elon Musk and several others, with PayPal. And all PayPal was a little gizmo that worked on the internet to allow people to buy things safely. So here is somebody whose fortune was based on the development that was done in those 40 years. The problem, the reason they never refer to it, is that that development was all done on taxpayers' money, by state organizations and taxpayers' money. And that's why they pretend that the internet grew on a tree somewhere, okay, instead of was developed. It's just incredible that he thinks that there was no innovation over those 40 years. I can't believe he really does think that. Now, I've already mentioned that Elon Musk and SpaceX come from that school of thought. They came from Elon Musk was part of PayPal, and also PayPal funded, by coincidence, really a bit, Facebook. He gave Zuckerberg his money to get Facebook started and a lot of advice. And interestingly, Zuckerberg, something he said was used as a motto by Facebook right up until 2014. And that was move fast and break things. It came from a quote, move fast and break things. Unless you're breaking stuff, you're not moving fast enough. And that was a quote from Zuckerberg himself. And at this point, I can't resist showing you a cartoon from Randall Munroe of XKCD. He's brilliant, absolutely brilliant. So you have somebody here at a job interview saying, my motto is move fast and break things. And then a list of jobs he's been fired from. And it's a list of things that you really don't want people to have the motto move fast and break things, like your dentist and your surgeon and dog walkers and museum curator. I love Randall Munroe, he's brilliant. Okay, so why am I talking about move fast and break things? Well, it happens to be an excellent description of something that we call hypervelocity. And hypervelocity is more than about 3 kilometers a second. So let's put that in context, okay? Fastest human that I know of is Usain Bolt, okay? And so that's about 0.01 kilometers a second. So hypervelocity is something faster than 300 volts, okay? Fastest cyclist that I know of is Mike Cavendish, well, arguably so. And hypervelocity is more than 150 kavs, basically. If you like motor racing, it's about 30 Mansells, top whack down the straight, okay? and, if you like, planes. The fastest thing that man has ever built is a fighter plane. It's the MiG Foxbat, and even that it only went at a third of the minimum speed for hypervelocity. So nothing in our experience prepares us for what hypervelocity means. Let me emphasize that. This is a road sign I saw in France. The idea is to get you to slow down by reminding you that the energy that you have goes to the square of your velocity. And of course, in a crash, that energy has to be dissipated. So if I plot for just a grain of sand and I take speeds up to hypervelocity speeds, more than 3 kilometers a second, in particular up to 18, which is the sort of relative velocities we can get in interplanetary space, then just a grain of sand, their energy rises like this. And up at the far right-hand end, that grain of sand has got more energy than a bullet fired from a high-velocity rifle. Okay, just a grain of sand. And that's why grains of sand can do enormous damage in space. These bullet holes are actually grains of sand that have hit solar panels that were on spacecraft in space. And the one on the right is actually from the Hubble Space Telescope, and it was recovered by the shuttle during the repair mission. Now, unfortunately, one of the solar panels was so warped that they couldn't put it into the hole of the shuttle. So Katie Thornton here, she just released it into space, and it flew rather gracefully for a while to burn up in the atmosphere. Kind of just adding to the space junk problem, but they had no option in that case. But we need to talk about that a bit more, and I'll come back to that. But let's go back to something a bit bigger than a space grain of sand. And I'm going to take a cube of aluminium the size of a sugar cube. Okay, so 1 centimeter cube of aluminium, and take that up through the same velocity. And by the time I get to 18 kilometers a second, it's got more energy than the most powerful hand grenade we have ever made. And so the ability of a small bit of metal like that to destroy a whole spacecraft is obvious. So where do we put spacecraft? Well, these are all places in deeper space where we can place spacecraft. They're called the Lagrange points, and they're particular features of the combined gravitational pull of the sun and the Earth. And L3 is no use to us because we can't communicate with it, because we can't get radio waves around the sun to talk to it. But L1 is very useful because we can look at the sun from there and we can see what it's throwing at us in terms of light and heat and particles. L2 is very useful because spacecraft there can look away from the sun and the Earth and all the light and radio noise that they cause. And L5 is actually rather useful because the Earth spins from L5 towards the Earth, and so we get advanced warning of features on the surface of the sun that might cause us problems from L5. So L5 is useful. But all of these have so few spacecraft at them that junk isn't really a problem, and I'm not going to talk about them again. I am going to talk about near-Earth orbits, though. Now, near-Earth orbits, every orbit can be described in terms of 6 different parameters. I'm not going to go through them now. I'm just going to pick some classes of these potential orbits, and here they are. The one in mauve is low Earth orbit, LEO, okay, and we use this for Earth observation. Spacecraft take about an hour and a half to orbit the Earth from a typical altitude, and the altitude doesn't vary very much. They're nearly circular orbits, and it's very, very crowded. There are mid-Earth orbits that can have a high inclination like this blue one. You'll notice that they're very elliptical, and the furthest distance from the Earth, the apogee, is much, much greater than the smallest distance, the closest approach, which is called perigee. This blue one's at high inclination, and we like that for space science because we can do things like observe aurorae, because that happens over the poles and things like that. Mid-Earth, mid-inclination or low inclination ones like this orange path. That's what we use for our GPS satellites and things like that. And then green is a circular orbit in the equatorial plane at a special distance, 6.6 Earth radii away from the center of the Earth. And that's special because the orbital period there is 24 hours. So a spacecraft there stays over the same part of the Earth and rotates with it. And that's really useful for broadcasting and communications and things like that. That's a very crowded bit of space as well. So those are the orbit classes. Now, where does all this space debris and junk that we worry about come from? Okay, well, the first thing is the obvious thing of collisions between spacecraft. They could be operating or they could be defunct. They could be no use to anybody, but they're still flying around there. And they crash together and that produces a lot of debris. Okay. Leftover rocket stages and fuel tanks are again something we can crash into. But even a defunct craft just left in space will eventually just explode because you've got fuels and fluids in tanks that expand and blow the tank apart. Batteries deteriorate and they explode. So craft just explode on their own, basically. We vent fluids and gases from rockets and they freeze, and those at hypervelocity speeds, those chunks of ice are very dangerous. Even dust gives flecks of paint off spacecraft, which actually, if they hit an astronaut on EVA, spacewalk, extravehicular activity, as the Americans call it, that would puncture the spacesuit and kill them. Okay, so that's a fleck of paint, okay, at hypervelocity speeds. Very rare, meteorites and micrometeorites collide with satellites. Tools have been dropped from space on spacewalks, and actually I'll give an example of something that actually came right through to Earth that was dropped by an astronaut. Deliberate destruction Star Wars tests. We know about 5 of these, and I'll show you the consequences. And then lastly, and recently, I've said very, very rare, but actually I can only think of one. But the completely unnecessary. Putting a Tesla in space, really? It's just space junk. Okay, so I'm going to show you what space junk can do. These are 3 movies. Pay attention, things happen very fast, of what space junk can do. The first is just a defunct spacecraft just exploding. Oh, it's losing a few bits. As it gets older, it loses bits. Bang, there it goes. And now you've got something completely out of control that can spin into other spacecraft and things like that. The second is a very small bit of space junk, okay? A tiny bit, but it's enough to cause a lot of damage and it's gone out of control. And this is a larger bit of space junk completely destroying a spacecraft. Those are all realistic simulations of what would happen. So we see the potential for generating space debris and junk, and we categorize it into 3 classes. It can be small, less than 1 centimeters, and we think, now these figures are about 2 years old, about 128 million pieces of small junk like that 2 years ago. Medium, 1 to 10 centimeters, and we think about 1 million pieces in low Earth orbit. And these largely come from collision debris. And then large, which is more than 10 centimeters. And we actually know the number there, we track them. And in June 2023, so that's nearly 3 years ago now, we knew of 37,000. Okay, I haven't got more recent figures than that. And then there's huge. Things like this. This was Envisat. It was as big as a bus, which makes these humans down here underneath working on it rather braver than me, given the way it's perched there. It weighed 8 tons up the surface of the Earth. It was an Earth observation satellite launched and orbited near about 800 kilometers. And we lost control of it, possibly space junk, but eventually we couldn't control the motors and it used up all the fuel. And that fuel was meant to deorbit it. I'll explain deorbiting in a moment. And we couldn't do it because the motors used up all the fuel. And now it'll take 150 years to re-enter, which just sounds okay, we'll worry about it then, but actually it's a worry now because every year 2 big pieces of space junk pass within 200 meters of it. So sooner or later we're going to have a collision, and that's going to be a big source of yet more debris of all sizes. So we have problems. This is the total number of objects in near-Earth space up to 2023. So it starts here with Sputnik 1, and this is the total number in black. In gray here you have debris, okay, tracked pieces of debris. This is the 37,000 I mentioned. The red is the number of operational crafts in space, and this big rise here is essentially Starlink and other constellations. So, and there are rocket boosters and things that have generally added to this. So the thing that catches the eye are these big steps in the number of bits of junk. I'm going to take this first one here because we now know this was a Chinese meteorological satellite called Fenyung IC. And actually, I was one of the first people to know that because I was using this radar that we just built in northern Scandinavia called the IceCat Svalbard radar. And we were commissioning it, we were testing it, and we were testing it by looking at bits of space junk as they flew overhead. We were pointing it towards the North Pole. And normally we saw stuff like this. These were all echoes we were getting off space junk. Blue was moving towards us, red was moving away. But there was we saw stuff going in all directions. This was from these heights, about 800 kilometers up and more. But then a week later, it looked like this, and we had stuff moving away from us and then towards us, and this pattern was repeating every day. So we knew something had happened, and we worked out that it was a path of debris. We could work out the inclination of what it had come from because, sorry, I'm jumping ahead, because of where the path lay. And we realized what was happening was that we were, at some time of day, as we looked towards the pole, we were seeing stuff coming towards us. Sorry. And a few hours later, we were looking in the opposite direction. Oh dear, sorry, I'm going to stop touching my screen. And we're seeing it going away. And we worked out the orbit, and then we looked up what spacecraft had been in that orbit, and we found an old Fenyung IC. And then later we found out what it was that it had been the object of a Chinese military Star Wars test, and it had been destroyed by what's called a ballistic kill missile, which is just a lot of metal, a bit of metal. And by July of that year, we catalogued over 2,000 consequent fragments of space junk. And that had consequences. For example, in 2013, one of those hit a Russian spacecraft that was working until it got hit, and that was destroyed by it. So there are consequences to doing this. It was an incredibly irresponsible thing to do. However, one cannot criticize people for doing what you've already done, because in September '85, the US Air Force had destroyed a lower altitude spacecraft in a missile test. So if you're going to do it, you can't complain when others do the same as you. It's something people need to remember. Okay, so that was that first blip. Let me talk about what happens to junk. I won't go through the equations particularly, but essentially what happens is that if I slow a spacecraft down, paradoxically, it speeds up, because what happens is it falls to a lower orbit. If it's got a lower speed, it has to find an orbit lower down, and in falling, it picks up kinetic energy and starts going faster. So it's kind of paradoxical that you slow a spacecraft down, it speeds up but drops in height. And that's how deorbiting happens, because spacecraft naturally run into the upper atmosphere, and that's always slowing them down a bit. So I've explained that. Oh, sorry, I'm going to let it, I should let it, let's do this, let the satellite do its thing. Sorry. There we go. So here it is. It's being slowed down, dropping in altitude until it burns up in our atmosphere. So that's deorbiting. And it happens naturally. It happens all the time. It's just the higher you start from, the longer it takes because there's less atmosphere to slow it down. We talk about two types of deorbiting. There's controlled deorbit, where we've got a bit of what we call delta V, propulsion left in the spacecraft. And so we can use that to slow it down and decide where it comes down, okay? And try and map where it will come down. And that's not just a matter of where it comes down along the orbit path. For that EnviSat satellite, it was in what we call a sun-synchronous high inclination orbit. And that means that the Earth is actually rotating around underneath it. So its path actually moves. So depending on which orbit it's on when it finally comes down, it could be at any longitude and it could be at any latitude, depending on the exact timing. So it could literally come down absolutely anywhere if it's uncontrolled. And as I say, we have no fuel left on EnviSat, so it will be uncontrolled when it finally happens, unless we do something about it. And then there's controlled or uncontrolled. And if it's uncontrolled, then we have no delta V, and we just have to, it'll come down where it comes down, okay? And that could be anywhere. So that is a worry, okay? Let me talk a little bit more about these steps. This was a second step here, was a collision. It was a collision between one of the Iridium constellation of satellites and the Cosmos, a Russian satellite called Cosmos 2251. And there's actually an animation of it here. So here are all the Iridium spacecraft. Here's POR 33, and there's the collision. And these are tracked, not to scale compared to the Earth, but those are the bits of debris. And you can see it formed two parts of debris, and their paths very much reflect the initial paths of the spacecraft, but the debris spreads out over time, okay? And if we just watch those red dots, they just add to all the other bits of space debris that we're tracking at the moment. So you can see it just contributed to the problem. This is a movie that shows you how close together things get. So this is the separation in the vertical axis, 20 minutes scrolling past you, and I think 10 times, or it's a 3-hour window scrolling past at 20 times real time. And the different colors are whether they're active spacecraft or bits of junk and things like that. But you'll see some are getting remarkably close together. Those were 2 active spacecraft there that got within a kilometer of each other. Okay, this was you can monitor this going on in real time. So it's quite scary how there's a bit of junk getting very close to another bit of junk. That's what yellow means. So that's happening all the time. So now people say, well, doesn't this make the space station a risk? I just need to look at my time. Okay, I'm doing all right. Yes, the space station has what we call a Whipple shield that can protect against small bits of junk. It essentially slows things down by putting it through a series of barriers so that by the time it hits the shell of the space station, it's slowed down enough that it doesn't actually penetrate it. And that will work for things up to about 1 centimeter in size. But anything bigger than that, we have to monitor things that are in the way of the space station. They're likely to hit it and just maneuver out the way. And what we're finding, of course, is as the number of space junk items goes up, we're having to do more and more of these maneuvers, particularly at sunspot maximum, for reasons I'll talk about. So we do have to worry about it for the space station. And really, they're just dodging the bits of junk, the bigger bits of junk. That's all they can do. What we worry about is something called the Kessler syndrome. This is was an idea, goes right back to 1978, and Donald Kessler was a NASA scientist. And he said, look, if you start getting collisions frequently enough, those bits of debris will collide with others, and eventually you have a runaway debris problem and space becomes unusable because of space junk, okay? And it would certainly, it might not make space impossible, but it might make it impossibly expensive. The insurance you'd need to put anything in space and the risk to humans in space would be just too great. So it might make it too dangerous and uneconomic to use space rather than make it impossible to use space. And some people believe that Iridium Cosmos collision was the start of the Kessler syndrome, that it's actually started, that we're on the way. Okay. And we find that we need models that are not just simple models. We need to take into account the altitude of the junk. Otherwise, we get a misleading picture. And we do find that we can get exponential rises at higher altitudes if we don't take into account the effect of space junk. So the worry really is higher altitudes. These are some simulations based on some scenarios. The blue is if there were no further launches in space, this is the amount of space junk there would be. These separate lines are different runs of the model, and then the thick line is the average of them. Okay, so it's what we call ensemble modeling. If we just extrapolate what we're doing at the moment, then we're beginning to get this exponential rise in the numbers of junk. It does go up and down with the sunspot solar cycle. Whoops. Okay. And if we are optimistic about our attempts to control space junk with proper deorbiting of space, when something we've put in space, we make sure we take everything back out of space again, then we will still get a rise, but it will be a limited one. But at the moment, we're on track for the red. Okay, so this is why I think we need better space law to actually protect our near space environment. The problem is actually worse at higher altitudes because the atmosphere is so much thinner up there, and things that are up there stay there much longer. Okay, the lifetime goes up quite dramatically, as you can see in this graph. So we need to worry particularly about things high up, although there's a separate worry about things low down. Notice Starlink satellites are really quite low down, and so they do re-enter quite quickly, compared to things like Iridium and things where they have a much longer lifetime up in space. Right. One thing that folds in here is climate change, because climate change is caused by, we know, everybody in science knows that it's caused by trapping in heat with greenhouse gases. And one of the key signatures of that is that the troposphere, the lower atmosphere, warms up, and the upper atmosphere cools. And you can see that in this plot. The red is warming part, and the blue, the stratosphere, is cooling. Okay, these are plots as against pressure level, which is essentially height, and latitude. And they're 4 different sets of data, and they all show the same thing. And that cooling is actually allowing junk to last longer higher up because there's less atmosphere to actually bring it down. So climate change is actually adding to the space junk problem because stuff is not re-entering as quickly. How can we mitigate for it? Well, there are a number of proposals for capturing space junk and bringing it back down. For geostationary, we have no real solutions. All we can do is, when a spacecraft is dead, is move it out to what we call a graveyard orbit outside the geostationary ring and hope none of the debris comes back in to affect us. Mid-Earth orbit, we have no clear solution. And low orbit, we do have this idea of deorbiting, where we actually capture a spacecraft and make it deorbit and burn up in the atmosphere. That has its problems. There are a number of missions that have, well, in the UK actually, our removed debris satellite is one of the first to actually demonstrate a technology that actually works. And ESA has Clear Space 1 and things, different ways of capturing objects and pulling them down in orbit. So how does it work? You capture it. So here's your junk going around. You come up behind it with your cleanup craft and capture it. And then you fire a rocket to slow it down. That means the 2 of them start to decay in orbit. Then you let go, take your cleanup mission back to find another bit of junk while the first bit of junk burns up in the atmosphere. Okay, so that's something that we can do to try and help the cleanup of space, which we desperately need. Junk, when a spacecraft breaks up, when it reorbits, it doesn't actually all come down at once. So things like solar panels break off and burn up first, and they'll come down quite soon. But later, the big core of something like the space station, this is a simulation of the space station being deorbited, it will come down much later, and it might even come right through the atmosphere and hit the ground. I'm beginning to run short. I just really want to make the point here. These spikes here are what we call geomagnetic storms. These are storms that give us the wonderful sights of the aurora, like May of 2024. But they also heat the upper atmosphere. That increases the density at a given height. That makes satellites reorbit. And in fact, that storm in May 2024 caused all these Starlink satellites, which were actually being lowered, ready for deorbiting, but they all re-entered shortly after the storm. It was a nice demonstration of how storms cause things to re-enter. I'll skip that. This just shows you the heating of the thermosphere in response to a space weather event. Okay, the power comes in at the auroral oval, but then spreads around the globe. And this shows you predictions for a cold, unheated upper atmosphere here, and then one heated by a space weather event. The heated one, things come down much quicker. When they reach about 120 kilometers altitude, they're going to re-enter, and they fall to Earth quite quickly. Okay, but it happens much sooner if the atmosphere is heated. And if you think about it, this can be several orbits of a low altitude spacecraft. So we really need to know the state of the thermosphere if we're going to predict where things are going to come down, and therefore make them come down. Now, the big concern is commercial constellations, because the numbers of craft that are going up, okay? And there's Starlink, but there are others that are planned, okay? Now, Starlink, they do have propulsion to avoid collisions, but it's not automated. They have to have radar tracked collision predictions telemetered up to them, and then they can move around. And then at the end of life, they lower the orbits, and so that they can come down. For astronomy, Starlink's extraordinarily bad news. This is a picture of Starlink satellite tracks across the sky. So it's really messing up a lot of telescope images. So astronomers hate all this stuff. And some things make it right through to the ground. This was a ring at New Year's Eve last year that fell down, or the year before last, New Year's Day, last year. It fell to Earth in Africa, just outside a village. Amazingly, nobody was hurt. It is certainly from space. It wasn't being tracked, amazingly. So we think it was in a kind of probably a skimming low altitude orbit. But other bits of junk that were found around it tell us that it was definitely from a spacecraft. It's almost certainly a separator ring from a rocket launch. But that's not the only thing. It was in Kenya, that's right. There's a family in Florida who are suing NASA because a bit of space junk that was discarded from the space shuttle fell through their house. It missed a child that was playing by about a meter, and it went through the ceiling, through the first floor, through the second floor, down into the basement, and made a huge hole in the concrete in the basement, in the floor. Okay, and as I say, it missed a child by about 2 meters. So they're suing NASA, and in what's seen as a bit of a test case for this. And SpaceX rockets parts are repeatedly falling to ground, and that has caused flights and things to be cancelled. Particularly Qantas have a lot of these things are re-entering in the southern hemisphere, and their flights have been particularly affected. And of course, when there are rocket failures, then flights around the Caribbean have to be cancelled and diverted. So these things, because a bit of space junk hitting one of these things will be lethal. And there have been examples of aircraft windshields being smashed by tiny bits of space junk that have made it through the atmosphere. But I'm going to end with perhaps the most worrying thing, and that's ozone. Now, the ozone hole and CFCs was a complicated catalytic chemistry whereby chlorine destroyed ozone. Ozone is very vulnerable. We rely on it to keep the ultraviolet levels low on the surface of the Earth, but it is extremely reactive, and so it's very easily destroyed. And we were getting ahead of the ozone hole destruction of it, but that seems to have come to a stop. And the worry is that it's space junk is the problem, because the metals that burn up in space when space junk burns up, and remember, all our deorbiting strategies rely on things being burnt up in the atmosphere, but those metals are extremely, the chemistry says they will destroy ozone. We don't have evidence that it's happening yet. We do have evidence that the metals are beginning to collect in the stratosphere. So there is big worry about this. And I'm going to end this talk with perhaps, for me, the most unlikely bit of praise. This surprises my friends a lot, but I'm going to praise this woman. Okay, there's lots I'm not going to praise her for, but she did give, I believe, one of the most important and best speeches ever made by a British Prime Minister in front of the United Nations. It was co-written by a friend of mine, as it happens, but she still gave it, and she understood the need to give it. And her quotes are quite often selectively, when she's quoted, it's quite often selected, like Frederick Turner and Adam Smith and people like this. But she said in that speech, we should always remember that free markets are a means to an end. They would defeat their object if by their output they did more damage to the quality of life through pollution than the well-being that they achieve by the production of goods and services. She was specifically, what caused her to actually say that was that she understood, she was a chemist, she understood the chemistry behind the ozone hole, and it horrified her, and the humanitarian consequences horrified her. We could really do with somebody like Thatcher, who could understand that this science is important. So I shall conclude. I'm not sure how much I've overrun by. Oh, not by much. Good. Okay. So my conclusions are: space is an incredibly valuable resource. We must look after it. We need safe, controlled deorbiting. And to do that, we've got to actually understand the state of the upper atmosphere. And to do that, we need space weather forecasts, because the upper atmosphere is very dependent. I've just noticed a spelling mistake. It's very dependent upon space weather. It's very fragile, and it will not survive irresponsible exploitation. And we urgently need new international regulation to actually prevent that from happening. And the possibility of the humanitarian catastrophe of ozone depletion means that we must apply the precautionary principle, and that is back off and go slow until the science tells us what safe limits are for deorbiting space junk. Okay, so with those conclusions, I'll stop. Anya, I've only run over by about 3 minutes.
You haven't. We said 45 to 50, so you've done really well. Thank you, Mike.
I've been gaining